Alright, how's everybody doing today? This is Mr. Muscarella coming at you, and we're going to take a look at another example of improper integrals. Now in this example, we're going to take a look at stating why the integral is improper and determine if it's divergent or convergent, and then evaluate the integral if it does in fact converge. Now this one's going to be a little bit different than our last example because right here in between 0 and 2 we've got an issue. If we plug in 1, of course we end up with 0 in the denominator, and 0 in the denominator is bad. So what we're going to do is go ahead and split this up. We're going to have this infinite discontinuity at x equals 1, and this is going to require a technique where we're going to separate our integral. Now if we take a look at this graphically, alright, so we're going for, this is one I like to call the volcano. So we've got 1 right here, and that's where our infinite discontinuity is. But we're going to be taking a look at the left side of it and the right side of it, but only up to 2. So we're going to cut this thing right off here, 2. So when we're really evaluating, we're trying to find the area of our integral. That's what an area, or that's what an integral is. You're trying to determine what the area is. So we're going to have two different pieces that we're going to take a look at. One's going to be this left piece, and then the other is going to be this kind of right piece. And both pieces shoot up forever and ever as you approach 1. Now we are approaching 1 from two different sides. Between 0 and 1, that's on the left side of 1. And then of course between 1 and 2, that's on the right side of 1. So keeping that in mind, as we separate our integral, that's what's going to give us this piece right here. So we're going to separate the integral into these two pieces, between 0 and 1 and 1 and 2. That's the first step that you're going to want to show. Now after you do that, of course 1 is where we're going to have our issue. And since we have an issue at 1, we're going to use the limit process to evaluate this. And when we do that, we're going to replace our infinite discontinuity, which in this case is 1. We're going to replace that with an a. So we're going to have a's go in wherever there's a 1. And on the left side of a, so that's between 0 and 1, so that's why this piece right here does have that 1 with a little negative. That implies that it's from on the left side. So we're going to have that piece there, and then on the other piece, of course, we'll have 1 from the right side. So our a's both are what are going to replace the number 1. Now from here, it's just going to be pretty straightforward evaluating an integral. So when you evaluate the integral, don't forget, make sure you keep the lim piece out in front, the limit component, as a approaches 1 from both the left and the right sides. When you substitute in a, now keep in mind, a is approaching 1. So when you plug in 1 to this very first one, you're going to get 1 minus 1. So if you do 1 minus 1, that's going to give us this 0 right here. All right. And then if you plug in 0, of course 0 minus 1 is negative 1 times 3. So 1 times negative 3, that's going to give you this piece right here. Now for the other component, the other piece over here, when you plug in, this time a is going to approach 1, but this time from the right side. So on that piece, when you plug in 1, 1 minus 1 is 0, and that's going to give us this guy right here, of course. And then when we plug in 2, 2 minus 1, of course, is 1, times 3 is 3, so that's going to give us this piece right here. So now it's just a matter of simple arithmetic, so just make sure you do that right, and when you evaluate that, you just get 6. Now since we actually get a number here, then we say, the integral converges to 6. So the area underneath the curve of 0 to 2 of 1 over x minus 1 to the 3/2 power, that area is going to converge to 6. All right, thanks for watching this example, and I'll catch up with you guys later. Peace out.